I'd like to thank all the organisers for inviting me to this meeting. It's been a real pleasure to have such an eclectic mix of people, and I've particularly appreciated the fact that the talks have been broadly accessible, and it's my hope that mine will also be broadly accessible. I'm going to talk about the topic of blending mathematical models with data. We perhaps all have a slightly different interpretation of what we mean by a mathematical model. So just to be precise, for the purposes of this talk, by mathematical model, I'm going to mean something which has predictive capability and is based on mechanistic understanding of the things that we see in data. The work I describe will be partly a history of the subject, partly a personal perspective based on some problems I'm working on with many different collaborators who I'll name as we go along. And it's been funded by many different agencies, all of whom are listed there. So I thought we'd start with the take-home message, and this is that mathematical models really matter. We're in the era of big data, and there's a lot of hype in newspapers about how data tells us everything. But the case I want to make, and it's been made by others over the last couple of days, is that the mathematical modeling which we use to incorporate the data really does matter. And if the mathematical models have predictive capability, and in many cases they do, the combination of data and model is very powerful, much more powerful than just blindly using data. So to take that a little bit further, we should use data, but we should use it to inform the parts of the model that are unknown to us. And this was something that Gita also emphasized in her talk yesterday. So that's what I hope to convey. The way I'm going to do that is by a little bit of history, talk about the subject of how data has been used in mathematical models over the last 1,000 years. Talk about how that has started to change around the turn of the century, and then discuss a little bit about the future. This will all be fairly general without too many equations, although I will show you some mathematical models in passing as we go through. Then I'll describe some principles that unify everything I've described, and then I'll work through a specific example which actually relates to the previous two talks concerning classification. And there are lots of references at the end which I may not get time to highlight, but the talks are going to be publicly available, and so you can find them there. So let me talk a little bit historically about how data has been used in mathematical models. And what I'd like to do is start with Newton. So one way of thinking about Newton is that he had one piece of data, which is that an apple fell on his head. And on the basis of that one piece of data, he developed a way of thinking and modeling the world, which has been enormously important for the last several hundred years. He was around in an era where was not the era of big data, it was the era of very sparse data. And yet the data mattered. The apple falling, at least perhaps apocryphally, led him to think about gravity and formulate his theories of gravity. Of course, that thinking, that data came in the context of a lot of conceptual thinking that had gone before him. He was standing on the shoulders of giants. And but this led to ideas of conservation laws, conservation of mass and momentum in particular. And those laws underlie things that I'll talk about going forward, such as weather forecasting, which Sebastian talked about yesterday. And a further important point to appreciate about the role of data is that from these laws, which have incredibly great predictive capability if used appropriately, data plays a role in specifying some of the constants that appear in these laws. So, for example, the viscosity of a fluid such as air flowing past a wing, that's an unknown constant which appears in Newton's laws of conservation of momentum, describing flow of a fluid. But that constant can be measured through experiment, and so data can be used to inform the model. In this case, the data is used in a very precise and direct way to measure the parts of the model, in this case the viscosity, which are not known. So the way in which models and data interact is rather simplistic. The models are developed on the basis of conceptual thinking. Some constants are unknown, and experiments are performed to fit those constants. Okay, so Einstein came a little bit after Newton, and there was an awareness that, for example, Newton's theory of gravitation didn't accurately predict aspects of Mercury's progression around the Sun, and in particular the precession of the perihelion, the closest point to the Sun. And this is an example of a data point which motivated thinking outside of the box of Newton, and amongst other pieces of data, led to the theory of special relativity, which improved the prediction of Mercury's precession of perihelion, and general relativity, which really nailed it. But again, Einstein was working in a context in which the data was sparse, and he was using small amounts of data, and using them to inform complicated models with excellent predictive capability. And just as an example of that, gravitational waves, which were predicted by him in 1916, were not measured until nearly 100 years later. So that as an example is something which should be contrasted with machine learning, about which we're all incredibly excited, but which, as measured by this kind of benchmark, has zero predictive capability. Most of what machine learning is doing is interpolating massive data sets. The predictive capability within those methods is currently incredibly low, unless you try and predict things that relate to data very close to the data on which it's trained. So again, Einstein's theory predicted things that we couldn't even measure for 100 years after. So these are, I'm saying these because, telling you about this because these are parts of our thinking as a human race which are incredibly powerful and are based on mathematical models which build into them understanding of the world around us. Now, towards the turn of the century, as we're all aware, we started to accumulate a lot more data, and that is impacting the way we think about modeling the world around us. And an excellent example of that is numerical weather prediction that Sebastian described in his talk yesterday. So let me just say a couple of things about that subject and contrast it a little bit with the way things were in the times of Newton and Einstein. There is a vast amount of data. Here are some examples of data that's used to inform numerical weather predictions. Weather balloons, commercial aircraft collect data which they give to weather forecasting centers, satellites, and there are numerous sources of data, so the data is very heterogeneous. The models are discretizations of Newton's laws, conservation of mass, and also mass momentum, and also energy. And there's a lot of data. On the order of 1 million data points are used per several hours. But the models are even bigger. So the number of unknowns, the number of state variables in a global numerical weather prediction model are on the order of billions. Okay, so there is a large amount of data, but the models are even bigger, and the models are based on physics that's pretty well understood. I'll show you some equations in a moment. Climate modeling is somewhat similar, but there are important differences. So in climate modeling, the goals are to predict more average or statistical quantities on much longer timescales than in numerical weather prediction. The basic physics is much the same, but because of the longer timescales on which predictions are made, there are differences. So the size of the data and the models are somewhat similar, but in numerical weather prediction, the primary goal is to estimate the initial condition and mitigate the effect, the butterfly effect, which was discussed after Sebastian's talk. The better the estimate of the initial condition, the longer range the forecast. In climate modeling, we're not really so interested in the details of the current state, but there are unknown parameters in these models, and we'd like to learn about them from data. So for example, because climate modeling requires integrating over much longer timescales, the resolution of space, the spatial variable, is much coarser than in numerical weather prediction. As a consequence, things like clouds or ocean turbulence are not resolved at all. They're not fully resolved in numerical weather prediction, but they're far less resolved in climate models. And they are parameterized, which is a subject Sebastian also discussed yesterday. These parameterizations aim to capture the physics that goes on beneath the grid scale, but they have unknown parameters. And in contrast to what I described yesterday, not yesterday, on the 2 slides ago regarding Newton, the parameters in, say, like viscosity in a fluid can be directly measured through an experiment targeted to capture what the viscosity is. The parameters that describe cloud models are not physically measurable, and it's not even clear that they have a real physical meaning. They capture gross physical quantities, but they cannot be measured. And so the way we learn about them are through indirect measurements, for example, satellites. And there's also the possibility of using high-resolution simulation at a small scale to improve those parameters. So this is an area in which the use of data has perhaps not been as important as it had been in numerical weather prediction, but where we're going to see more progress in the next decade or so. So let me just show you flash up some aspects of the mathematics that underlie both numerical weather prediction and climate modeling. This is the Navier-Stokes equation, which is the equation that describes conservation of mass and momentum arising from Newton's thinking several hundred years ago, but here written down in a continuum way that allows for spatially varying velocity and spatially varying pressure, which are coupled together in these complicated nonlinear partial differential equations. So just to give you some idea about where data comes in weather prediction and climate modeling, the actual equations are much more complicated than this, but this gives you some of the basic idea. There's energy equations describing conservation of energy as well, and there are different phases depending on whether water is in liquid form or not, for example, forming rain and clouds. But at the heart of the equations are things of this type. So what do we learn about from data? Well, as I mentioned, in weather prediction, the key goal is to learn about the initial condition. Where is this nonlinear partial differential equation initialized? We usually have very strong prior information about that from our previous forecast, but we also have observations, and we use these to make improved initial conditions in the way that Sebastian described. As I mentioned, in climate modeling, these equations are discretized, so these continuum differential operators are replaced by matrices, finite difference, finite element, or spectral approximations. And they have a lack of resolution down to small scales of kilometers. And beneath those scales, parameters are introduced to describe the physics. And those parameters are not known and can potentially be learned from data. So this is an example of a more general phenomena I'm going to show you with a couple of other examples, which is that the mapping from the thing you don't know, either the initial condition, let's just focus on weather, the initial condition. What is it that we measure? Well, let's say we measure aspects of the velocity field v at points in space and time. The mapping that takes us from the initial condition, which is the initial velocity field in the atmosphere, to later measurements of the velocity at points in space and time, that's a very complicated nonlinear mapping. Very different, and we'll come to models later, from the kind of linear models that we've seen in a number of the statistical problems today and some of the talks yesterday. That's not to say that those are not good models for those data sets, because in many of those settings in econometrics, there's much less fundamental understanding about what produces the data. So starting in a linear model is sensible. Here, though, we have centuries of knowledge which have led to this equation, and throwing it away would be stupid. So we are constrained by physics and how the physics manifests in equations which we have tested and know have good predictive capability. And therefore we're stuck with complicated mappings from the unknown to the data space. Okay? And that's a general theme that I want to press on with as we start to look at other examples. So I've talked about the previous millennium, turn of the century, and I want to start to look a little bit at problems that are going to dominate the future blending of mathematical models and data. And this is, as I said, this talk is a personalized talk in the sense that I'm going to describe collaborations that I'm involved with. So this is a collaboration to model type 2 diabetes and other things involving the human glucose insulin system, and is a collaboration with Dave Albers and Matt Levine, who are at Columbia Hospital in New York. So let me tell you a little bit about the data that's involved here. The motivation for studying diabetes is probably known to all of you. It's one of the most prevalent diseases in the Western world, and the costs associated with it are enormous, arguably the highest cost associated with any medical condition in the United States, simply because of the large number of people suffering from type 2 diabetes. Here is a number of pieces of data that I want to describe to you before I go to the model. Let me just concentrate on two of them. One is input. So people eat stuff, and that's input sugar, glucose, into their systems. So apps are being developed which enable sufferers from diabetes to photograph what they're eating, and through crowdsourcing of nutritionists to get an estimate of the content of the glucose level that they're just about to put into their system. So this is noisy data, but it's very helpful because it's crowdsourced based on people with expertise. At the same time, diabetics can measure their glucose levels either through finger stick measurements. Those are marked with circles on, with circles on this picture here. And there are also continuous glucose monitors that measure glucose as a continuous function of time. So there's a wealth of data available, and that data is increasing in volume. And a useful concept is that patients in all areas of medicine, this being one of them, should access their own personal data and be able to make use of it. So how might you best make use of it in this situation? Well, you'd like to understand how glucose and insulin interact inside the human body. And this is a situation which is much more complicated than modeling fluid flow past a wing. What goes on inside our bodies is enormously complicated, and there are many, many different models for how you would describe glucose and insulin and their interactions in the human body. I'm just picking on a relatively simple one, just to say that in this general context, one of the things we're doing is evaluating different models by their ability to predict real data, or to fit and predict from real data. This is just one of the models, and let me just describe roughly what it is. First of all, in contrast with the Navier-Stokes equation that I showed you earlier, this is a much simpler model. It has three ordinary differential equations describing evolution of plasma insulin, that's insulin in the blood, interstitial insulin, that's insulin in tissue, and glucose. So these interact through very reasonable laws which represent a number of things, such as the exchange between plasma and interstitial insulin, the reduction of glucose through insulin, and the production of insulin in response to measured or sensed glucose in the system. But these nonlinear functions here, F1, F2, F3, F4. The function Ig, which describes the uptake of glucose through eating of meals. All of these are A, not understood from a fundamental point of view, in the same, very different from our understanding of fluid mechanics, don't really have fundamental understanding other than qualitative for these functions. And B, even if you accept the qualitative structure of these functions, they contain parameters which depend on individual patients. So what can we learn from data? So this is a very personalized perspective. So the first thing, from the point of view of controlling the system, which means if you're a diabetic, knowing how to control how much you eat and possibly how much insulin to put into your body, learning the personalized values of the unknown parameters from your personal data is a goal for clinicians. Secondly, on a longer time scale, and this is more about the physiology and how that evolves in response to the disease, studying the evolution of these parameters in time is also of interest. So that means modeling the parameters as functions of time. And this is another point I would want to emphasize. I talked in the context of weather forecasting about estimating the initial condition, which is a function. It varies across the whole globe. Here, when we talk about the evolution of personalized unknown parameters, we're again interested in learning about parameters which are functions. So this is what was referred to in the first talk yesterday as functional data analysis. We may have data which is in the form of a function. That would be coming from continuous glucose monitor. We may also wish to infer things which are functions. So this is a second example, and so what I'd like to say in contrasting with the weather forecasting is that the volume of data is commensurate with the size of the model. In fact, the number of parameters here is much smaller than the amount of data. In contrast, in the fluid mechanics models I described, the number of unknown parameters is much higher than the amount of data. So these are rather different situations, and the model here is much less fundamental and believed in. It's much less of a strong constraint than the equations of Newtonian conservation of mass, momentum, and energy. Nonetheless, the general principle that we have complicated nonlinear mapping from unknown parameters to data, that persists. Okay, now going on further and more speculatively into what data might do for us over the next 100 years, we could actually start thinking about human behavior and how we might learn about it from data. Isaac Asimov, who was a science fiction writer in the 50s, wrote a number of things, but there are two books here that I highlight. One a short story called I, Robot, and one of three novels called Foundation, both of which had at the core things that were predictive of actually what has started to happen in our society. So I, Robot has the concept of laws which govern robotics. And of course, robotics is now a well-developed subject, and the incorporation of data by robots which have laws that constrain their behavior is precisely what is going on within self-driving cars and other autonomous objects within homes, so for example, or factories. So this is one area where we will want to combine data with models. More complicatedly, actually modeling human behavior directly. This was something touched on in this particular novel. These books are terrible, by the way, from any point of view other than the fact they were interesting scientifically, in my opinion. He was a terrible. I don't think he understood humans at all, but he was very good at predicting what might happen in science. Anyway, that's just my personal view. So in this context, the data is almost limitless. We're gathering more and more data, but we don't really have good models. I mean, what my personal hope is, and even a belief, is that over the next 100 years, as we gather data about complicated things like human behavior, we will develop complex models that have a predictive capability. But we're far from that at the moment. Now let me just touch on one example in this direction of predicting human behavior, which is work with Susana Gomez, who is a postdoc working with me and was a student of Greg, who is the next speaker, and Marie-Therese Wolfram, who is a professor at Warwick. We're interested in understanding human behavior in crowds. So this may not be entirely clear to you here, but what you're looking at is a bunch of people wearing funny white things on their heads. And the reason they're wearing funny white things on their heads is that this is a crowd, they move, and their positions are monitored through these things, on the white things that you can see on the top of their head. So this is an indication of a type of experiment that's being conducted to which enables the modeling of crowds not only as fluids. If you think about the mass of the crowd, you can think of it as flowing like a fluid, but also what individual people do within a crowd. The model that Susanna and Marie-Therese and I are working on is a model adapted exactly to this kind of data situation, in which there's both a mass of people which flows, described by a density rho, which satisfies a partial differential equation. And there's an equation which is a stochastic differential equation for the motion of an individual within the crowd. And that's this stochastic differential equation here. And the stochastic differential equation depends on the individual's sensing of the crowdedness of the environment around him or her. So this rho captures the crowdedness. It's the density of people around. And it's evaluated at the location of the person in question, and it appears as a drift in a stochastic differential equation. And the hypothesis in our work is that by monitoring individuals in this crowd, we get trajectories of this stochastic differential equation, from which we can potentially learn the form of the function f, which describes the motion of the individual in a crowd. Okay, so the function f is sometimes referred to as the fundamental diagram, and the model we are using is taken from a model of traffic flow that was developed by Whittam in the 1950s, and we're here transporting it to human flow. So again, we have this stochastic differential equation coupled to a partial differential equation. So this is a nonlinear Fokker-Planck equation, for those of you that know stochastic differential equations, and it's nonlinear because it depends on its own density through f. So what can we learn from data here? Well, we can potentially learn the parameters of the fundamental diagram, which is postulated to be a way of describing how individuals move within a crowd. And we can study the validity of this model and compare it with other more complex models. Again, the mapping from the unknown parameters in f, which I denote by theta, to the data, which is a time-continuous trajectory of this stochastic differential equation, is a complicated nonlinear mapping. And we're stuck with that. And to make inversion and inference about theta, we have to work with that complicated nonlinear model. Okay, so in all three cases, the fluid flow arising in modeling of the weather, climate, in the modeling of diabetes, and in this modeling of crowds, a unifying principle is that the mapping from what you don't know to the data is complicated and describes mechanistic principles which are believed to describe the phenomena that give rise to the data. And just to revisit it, the fact that those mechanistic principles have predictive capability is incredibly important and needs to be respected in the learning about data. So I like this kind of picture here. So this is as you go down here, the models become less and less believable. So in physics, there are a number of laws which we almost believe 99.9% to hold, at least in certain regimes. So conservation of mass, momentum, and energy, and the particular manifestations of them in, for example, the model of fluids or solids. These are almost accepted as axioms. Quantum mechanics, likewise. So we have a strong belief in these models, and that must be reflected in any inference that you do. But the biomedicine, the problems I described, for example, in modeling of diabetes, these are good cartoons, but they're not based on fundamental principles. So they should be treated as weaker constraints on the blending of data with the model. And as we went into social sciences, the particular model I wrote down is a pretty weak cartoon, I would say, of human behavior in a crowd. And in fact, part of what we're interested in is evaluating how good it is and whether one should use other models. And as you go into commerce, Amazon, Google, Netflix, the models are often really driven by the convenience of the data structure and ability to manipulate it. And as yet, there's very little understanding of what the mechanisms are that are generating the data. And there's I would say, no real predictive capability in this field, other than in the form of interpolation. And even there, the adversarial examples that Zubin mentioned yesterday show that even interpolation is fraught with difficulty. But I put the word yet here because humans are quite creative, and I believe that, in terms of mathematical modeling, this is the frontier. Finding mathematical models for these more complicated commercial or human applications, I think, is an area where mathematics has a lot to add, and data is not the final story. Using our understanding, thinking, to develop models will, I think, play a very important role in making big data usable. So I've been talking about models all the way through, and you might ask, well, what is a model? And up until now, model has been pencil and paper equations, which we write down and we sort of understand. We're indoctrinated about using them in high school and even earlier. And these define black boxes, which are input-output relations between, say, the side conditions for equations and what you get out of solving them. In the future, perhaps neural networks will define black boxes. Maybe we won't write down equations, but maybe we'll have understanding that there are different kinds of neural networks that represent different phenomena, and we'll be happy with manipulating those as basic objects that comprise models in the way that we currently do with, say, differential equations. That's speculative, but I think thinking about what we mean by a model and predictive capability is an important thing. So I'm going to talk a little bit about some general unifying mathematical principles that underlie the three kinds of examples I described. They're all inverse problems. Or you could think the whole of statistics is really about inverse problems in some sense. But there are some particular characteristics of the problems I described that I want to highlight. In general, we're seeking to find u, which may be a function, from y, which may be a function or may just be a finite collection of data. Depending on the setting, it may be useful to think either way. In many of the problems I'm interested in, however, it is interesting and important to think of u as being a function, and that's a coded way of saying, in practice, it's going to be very high dimensional, and algorithms which respect that high dimensionality are important. For simplicity, I'll assume that the data we're given is polluted by Gaussian noise, but that can easily be relaxed. Okay. So what are the issues? The issues is that the noise that pollutes our data is typically not known. The data y may not be in the image space of G, so even if we could invert G, we won't be able to invert it on y, because y is not an outcome of applying G to anything because of the noise. And so in some sense, there's no solution if you just try and invert G on y. On the other hand, in another sense, there may be many solutions. There may be many u which make y minus G small. Okay, so some form of regularization is needed, and as I said, there's references at the end that will enable you to trace some of the history of this. I'm going to talk about the optimization technique and the Bayesian technique to regularizing this problem, and just say a couple of things about those matters. So there are three key considerations that come about when you think about inverse problems like this. First one is how you regularize the problem. Perhaps these should be in the opposite order. An important one is how you parameterize, and I'll show you what I mean by that with an explicit worked example, and the choice of the algorithm that you use, which might be an optimization method or a Bayesian method. And these interact with what the purpose of your inference is and the computational tractability of what arises from this thinking. And overall, this leads to a way of thinking about combining models and data in a single conceptual framework. And by the way, I think that we should be teaching in applied mathematics, which is my field, we should be teaching modeling in the context of data and in the context of this picture, not thinking about models on their own and then data something you look at later, but rather conceiving of problems in terms of the data available and the models available at the same time. So in the optimization approach, remember we're trying to find u from y. So we, roughly speaking, want to make g of u close to y, so we try and do some least squares to minimize y minus g of u. That is typically not a good optimization problem in that there may be sequences of functions u which make this smaller and smaller, but the functions u become wilder and wilder and don't correspond to our understanding of what a u that solves this problem should look like. And that is dealt with through regularization. So regularization is something we've seen a lot of today in the L1 context. And I'll comment on how that links with what is here. Let me just give you a couple of regularizations that arise when u is a function, mapping a domain in d dimensions to the reals. So commonly used regularizations are the HS norm squared. This corresponds to differentiating u s times, and there's a concept of a fractional derivative which is sometimes useful. But roughly speaking, you differentiate s times and calculate the square of the sth derivative and add that as a penalty. That induces smoothness. On the other hand, there are problems where cartoon images, for example, where piecewise constant functions or piecewise smooth functions in which interfaces are penalized, therefore interfaces are not too sensitive to fitting data, noise in the data. A good penalty for that is this one here, the total variation norm. And this is, if you like, an L1 norm of the gradient of u. So it induces sparsity with respect to the gradient of the function. I'll come back to this in a few moments. Or we can so that was regularization via optimization. So we try and minimize this and add a penalty term. The probabilistic viewpoint is the Bayesian one, which I personally like, not because I'm a hardcore Bayesian, which I'm not, but simply because it's a modeling framework which makes explicit all of the components available to you in a situation where you have a model and data. So let me describe Bayes' theorem to you from that point of view. We want to find u from y, where y is g of u plus noise. So in the Bayesian framework, we describe what we know about u through a probability distribution. And I'll assume I can write that as e to the minus r. I'll come back to that in a second. The likelihood, so that encodes knowledge about what we think the solution looks like before we acquire data. The likelihood describes the model and how the thing we're trying to learn about u is related to the data. And then from the combination of prior and likelihood through Bayes' theorem, we compute the posterior distribution, which tells us the probability distribution of what we want to learn about, given the specific instance of the data that we've seen. So I've been interested in making sense of this way of thinking, which, as we all know, goes back several hundred years. I've been interested in making sense of it in the context where u is a function. You have a Bayes theorem, and it looks like this. So this just says that the posterior probability is proportional to the likelihood of the data multiplied by the prior. And okay, but so that is just Bayes' theorem, but there are a number of things that happen when U is a function. So in particular, we are able to make sense of the idea of a map estimator, which is the point that maximizes the probability. And the map estimator minimizes I, which is precisely the objective function that I wrote down in the optimization picture on this previous slide. So we've developed links between the classical optimization approach and this Bayesian approach, essentially by making sense of map estimator on function space. And we also have a stability theory about this Bayes theorem. Shows that the posterior distribution is Lipschitz with respect to the data in a particular metric on probability distributions. So there's a fundamental, if you like, theory which puts Bayes' theorem on a sound footing from which you can start to apply computational algorithms in a good way. And that emerges from this theory. And what I would like to do, if I have, I believe, a few more minutes, 4, is just finish with an example. So I'm going to do an example of classification, which links to the previous 2 talks. But before I get to classification, I want to just talk a little bit about parameterization because it's relevant to the classification problem. And in doing that, I'm going to make a link to Omar Gattas' talk yesterday. So he talked about learning about the subsurface through seismic imaging, for example, or well log measurements in an oil reservoir. And what you see here are typical descriptions of subsurface permeability as a Gaussian random field. And this is rather the exponential of these is a good way of, believed to be a good way of describing on long length scales the property of subsurface. On the other hand, on shorter length scales, we know the subsurface may have faults in it, layered structures due to the way that different geological ages deposit different material, faults caused by earthquakes and so forth. So there's geometry, which also one might want to represent in the subsurface. And if you represent it, you can represent it for problems of this type. The geometry can be represented by a finite number of parameters. Or here I have a channel. There are many historical riverbeds buried beneath the surface which give rise to channelized structures in the subsurface. Again, these can be parameterized by a small number of parameters. But there are lots of problems where the interfaces between different domains, we don't know very much about them a priori. And so this takes us into the domain of unknown interfaces. And this is an area which I'm interested in for solving physical problems, such as those Omar talked about yesterday. But what I want to do is just take this as a launching point for talking about classification. Because, okay, this could be the subsurface. The idea of the level set method is that you want to recover things that look like this, but that's not a nice place to work because these are discontinuous. And the idea of the level set approach is that you work with continuous functions and you apply a nonlinear mapping, in this case taking the sign, to compute a piecewise constant function. Okay? That's a very powerful idea in mathematics, and it's much more general than what I show here. Here I've just taken the sign of this function. Where it's negative, I've colored it blue. Where it's positive, I've colored it red. And then we invert on the top level and make inference about the bottom level. You can think of this as a classification problem. I'm classifying into red and blue. And in fact, I can classify into many more categories. And so I would just want to finish by describing applying the Bayesian technique to a semi-supervised learning classification problem that's a sort of classic, relatively easy test problem. Although this problem is usually looked at in the supervised learning context. So I'll describe the difference. So the MNIST data set is 70,000 images of handwritten digits, so 10 of them from 0 to 9. Supervised learning is typically based on using 60,000 of these images to train a neural net and then testing its predictive capability on the remaining 10,000 images. I'm going to do something weaker, semi-supervised learning, in which I I take 100 digits and label only those digits and try and learn the remaining 69,000, well, no, 69,900. And that can be done by applying the analog of this level set method. I don't have time to describe the mathematical details, but for those of you that wish to follow up, there will be a slide available to you. What I want to say is that from this, because we take a Bayesian approach, we can quantify uncertainty, and we can use that information to go back and label more digits. And I just want to finish by showing you that as I go through these three, I'm essentially doing a experimental design problem, and as I go from labeling 200 to 300 to 400, you see we reduce the uncertainty and the predictive capability of this the algorithm that we train. Okay, I'll leave the conclusions up here, and there are references for those of you that want to get the talk off the web afterwards. Thank you for your attention.
So thank you very much.